Hello everyone, welcome back to my tutorial on data pricing from economics to data science. This is the fourth part of the tutorial, pricing digital products. Although the focus of this tutorial is about pricing data products, I will provide a brief review on pricing digital products here, since some general ideas in pricing digital products can be borrowed and extended to data products. In some cases, the boundary between digital products and data products is even blurry, as we discussed before. In this section, we first discuss the three major streams of revenues for digital products. Then, we look at two major types of pricing models. The first is bundling and subscription, and the second is auctions. These pricing models are popularly adopted by digital product marketplaces. First, let's look at the streams of revenues. As discussed in Section 3, revenue maximization often serves as the basic objective in pricing mechanisms, including pricing digital products. Therefore, the understanding of pricing digital products has to start with an analysis of possible ways revenues of digital products may come from. Lambich summarized that there are three streams of revenue for digital products that are delivered online. The first is money. It means a provider can sell to customer content or more broadly services such as movies and ebooks. The second stream is information and privacy. Instead of charging customers directly, a provider can collect the customer information by tracking and sell the information about customers to generate revenues. Here, we may use, for example, cookies to track customers. The third stream is time and attention. A provider can sell space in their digital products to advertisers to produce revenue. Often, a firm has to design a revenue model for its digital products that combine more than one revenue stream. The three streams are not independent. Instead, they are competing with each other. And thus, a good trade-off has to be settled. On the one hand, in some situations, revenues from money stream may be increased at the cost of those from time and attention stream. For example, customers may pay for the content and avoid ads, or convert from free versions to premium versions with fitting functions. On the other hand, customers may be highly price sensitive in some digital products, and thus growth in time and attention stream may be easier. For example, an online news site experiences a dramatic loss of customer visits after introducing a paywall. Free samples may simulate long-term sales. A possible trade-off between money and time attention has to be carefully designed. Typical approaches in revenue models of content and services include rigid pricing. That is, for example, each movie is priced at a fixed price. Designing pricing tiers. For example, we may have basic versus premium versions. Setting up duration of subscription plans. For example, we may have 6 months of promotion period with very low subscription price, and then design freemium models. One important and unique feature in digital product consumption is micropayment. which means a customer can pay a very small amount that is typically impractical in traditional transactions using standard credit card due to the network service fees. Micropayments and subscriptions have different effects on consumer behavior. As a concrete example of revenue models, consider pricing software products. The major parameters of pricing models include formation of price, structure of payment flow, assessment-based price discrimination, price building, and dynamic strategies. The formation of price considers price determination, that is, cost-based, value-based, or competition-oriented, as well as degree of interaction. Unilateral versus interactive. In terms of payment flow, it may be by single payment, recurring payments, or combination. The assessment base of pricing may be usage dependent, such as by transaction or time, or usage independent, such as server times and GPU. As the tracking cost of digital products are low, a firm can collect customer personal data and sell such data to produce revenue. That is, we can generate revenue from information and privacy stream. Typically, personal data may include customers' identities, behavior patterns, preferences, and needs. There are various ways to sell customer data, which will also be discussed in Section 5 when data products and their marketplaces are discussed. For example, a website can provide direct marketing companies' user activity information. Moreover, websites can also collaborate with data management platforms like DMP for advertising and produce revenues by facilitating businesses to identify audience segments. As another example, the information about how customers are connected in social networks can be used to design customized discounts in marketing campaigns. There is a model to price customer-level information such that the data about each customer is sold individually and individual queries to the database are priced linearly. As new technologies of customer tracking become available, more pricing models may emerge. We want to point out that selling customer data, though serves the purpose of selling digital products, crosses the boundary between selling digital products and data products. We will review some studies on setting prices of customer data and privacy information in the section about pricing data products. To produce revenues for time attention stream, many digital product producers and service providers embed advertisements in their products in one way or the other, and obtain remarkable or even dominant advertising income. However, as John Wanamaker wisely said, half the money I spend on advertising is wasted. The trouble is I don't know which half. This is well recognized that it is hard to accurately measure advertising effects. Advertisers can customize ads for online display. In summary, Digital product and service suppliers produce revenues through three major streams: money, information and privacy, and time and attention. Orthogonally, a firm can bundle its digital products and also design subscription plans that provide products and services in a specific period of time. Bundling and subscription planning will be discussed next. As discussed before, the low replication cost of information goods allowed prevalent adoption of bundling. Product bundle organizes products or services into bundles, such that a bundle of products or services are for sale as one combined product or service package. Product bundling is a common marketing practice, particularly in the traditional industry like telecommunication services, financial services, healthcare, and consumer electronics. Designing product bundles essentially is a combinatorial optimization problem. The basic and static setting is that a customer wants to buy either one or multiple products at a time, which is investigated well before the digital products are available. A series of studies developed pricing strategies with two products under different various types of bundling. They share the basic assumption that demand of a bundle is elastic comparing to demand for individual products. For example, Armstrong studied the scenarios where products may be substituted or provided by separate sellers. Bundling multiple products is analyzed, often under the independent value distribution framework. Consider the situation where there are n heterogeneous products for one buyer, and the objective is to maximize expected revenue. Assume that the value distributions on products are independent, that is, for each product xi, the price that the buyer would like to pay for is an arbitrary distribution di in range from ai to bi, where ai and less than bi between 0 and they are finite, and those distributions d1, d2 until di are independent from each other. Further assume that the buyer is additive, that is, the buyer's value for a set of products is the sum of the buyer's values of these individual products in the set. Then, there's a study shows that either selling each item separately or selling all items together as a grand bundle produces at least a constant fraction of the optimal revenue. This interesting and important result shows a simple yet effectively bundling strategy, either pricing each product individually or pricing the grand bundle in the expected price. In practice, many platforms such as Lulu and Amazon Prime Video offer grand bundle subscription for their products. More recently, there is a study showing that grand bundle is optimal if customers with higher values of the grand bundle indeed have higher relative values for smaller bundles compared to the grand bundle. When multiple buyers are considered, those preferences are unknown. Bell can give a simple pricing model that achieves a surprisingly strong guarantee. In the case of unlimited supplies, a random single price achieves expected revenue within a logarithmic factor for customers with general valuation functions. This result allows great convenience in practice, that is, setting a uniform price for all products. It is easy to price a bundle of a larger number of products, since the law of larger numbers allows to predict customers' valuations for a larger bundle of products more accurately. Orthogonal to bundling, subscription is to price the interactions between customers and a platform over a period of time. Subscribing customers are in general heterogeneous in both usage rate and value of products. On the one hand, customers with higher usage rates may prefer subscribing to larger subscription sets. On the other hand, in order to maximize revenue, the platform wants customers with lower usage rates to subscribe and customers with higher usage rates to rent. Moreover, different users may have different values for a product. Many platforms offer subscriptions and renting at the same time. For a platform, the subscription model is to select a subscription fee and the period for each set of products, and also set the rental price for each product. Allais et al. Follows the model of grand bundle and consider grand subscription, a single rental price for the set that includes all products. They establish the sufficient and necessary condition for the optimality of grand subscription. They also show that subscription fees can be set proportional to the cardinality of a set of products and can achieve 1 over 4 log 2m plus log n of the optimal revenue of n times of customers and m times of products. This approximation is tight in the sense that it cannot be improved more than omega 1 over log n in polynomial time. After all, bundling and subscription modeling is computationally challenging due to the combinational nature. Dynamic pricing bundles and subscriptions, such as promotions and coupons, have rarely been touched yet. Now, let's move on to look at auctions. Auctions have a long history back to the Babylonian and Roman empires. There are many excellent surveys on auctions. A comprehensive review on auctions is far beyond the scope and capacity of this tutorial. In this tutorial, we instead only focus on the important role of auctions as a pricing mechanism for digital products. First, let's look at the basics about auctions. There are 4 basic types of auctions. First, in the ascending bid auction, which is also known as the English auction, the price is raised successively until only one bidder remains, who wins the object at the final price. The descending auction, which is also known as the Dutch auction, works the other way by starting at a very high price and lowering the price continuously until the first bidder calling out and accepting the current price. The third category is the first price sealed bid auction, where each bidder submits a bid without knowing the other's bid. The one making the highest bid wins and pays at the named price. Last, the second price sealed bid auction, which is also known as the Vickery auction, works in the same way as the first price sealed bid auction does, except that the winner pays only the second highest bid. There are two basic models of the value information in auction. The private value model assumes that every bidder has an independent value on the object for sale. The value is also private to the bidder only. The pure common value model assumes that the actual value of the object for sale is the same for all bidders. But bidders have different private information about the actual value. Every bidder adjusts her or his estimate of the actual value by learning other bidders' signals. There are also models considering both values private to individual bidders and common to all bidders. One fundamental principle in auction theory is the revenue equivalence theorem, which essentially states that for a set of risk-neutral bidders with independent private valuation of an object drawn from a common cumulative distribution that is strictly increasing and optimized on a range V mean to V max. Any auction mechanism yields the same expected revenue, and thus any bidder with valuation V making the same expected payment if two conditions hold. The first condition is that the object is allocated to the bidder with the highest valuation, and the second condition is any bidder with valuation V mean has an expected utility of 0. Based on this revenue equivalence theorem, the four basic types of auctions lead to the same payment by the winner and the same revenue. While most study in auction theory make some simple assumptions about independence of customer valuation, empirical studies demonstrate that, in practice, the wrong assumption of evaluation independence causes inefficient auctions in e-commerce. As a special and interesting case study, let's look at sponsored search auctions. One important application of auctions in pricing digital products is online ad and sponsored search auctions. Sponsored search is the business model where content providers pay each search engines for traffic to their websites. In sponsored search, advertisers and more generally content providers bid for keywords in search engines, and search engines decide which ad to display in which position to answer a query from a user. GoTo.com created the first sponsored search auction. Different pricing models can be used in sponsored search auctions such as pay per mille, pay per impression, pay per click, and pay per action. In the early days of sponsored search, a generalized first price auction is used. Each advertiser bids on multiple keywords and can get a bidding price for each keyword. When a user query, which is a keyword, is answered, the top K bids on the keyword in price are displayed. If an ad is clicked by the user, the corresponding advertiser pays the bidding price. The first price auction mechanism is unstable and costs advertisers time and reduces search engine profits. Later, Google generalizes the second price auction mechanism and enhances the ranking of bids by additional information, such as the ad's click-through rate, keyword relevance, and ad's landing side quality. There are many in-depth analyses about sponsored search auction mechanism. For example, some studies analyze auction mechanisms based on assumptions about rationality, budget constraints, and CTR distributions. Some other studies look at practical sponsored search systems and discuss auction mechanisms where the standard assumptions do not hold. Another group of studies conduct empirical studies to understand bidding behavior and statistics. Last and latest, deep learning approaches are used to develop auction strategies in sponsored search. Now, let's look at auctions on digital products with unlimited supplies, which is a unique and interesting problem to digital products. One unique feature of digital products is that the replication costs are very low and thus may have almost unlimited supply. Products of unlimited supplies bring new challenges and opportunities to auction mechanism design. For example, the second price auction can be straightforwardly generalized for k identical products. The top k highest bidders win and each pays the k plus 1th bidding price. However, when there are unlimited identical products, the k plus 1th bidding price approaches zero. The lack of competition due to abusive supplies prevents bidders from offering any high prices. In other words, the challenge is how to ensure the bids are truthful. That is, the bids reflect the bidder's true valuation of the digital products. Denoted by B, the set of bidders, and by B1, B2, the bidding prices in descending order. That is, we assume that BI is higher than BI plus 1, and of course, all the bids are positive. Suppose the generalized second price auction mechanism is used. That is, if K bids are taken, those winning bids each pays the cost B K plus 1. The option's objective is to maximize K times B plus 1. We say an auction is competitive if it yields revenue within a constant factor of the optimal fixed pricing. It is tricky that when there is an unlimited supply, the victory auction is not competitive if the seller chooses the number of products to sell before knowing the bids. And it is not truthful if the seller chooses after knowing the bids. Goldberg et al. Proposed the first competitive auction for digital goods. The major idea is the framework of random sampling auction. An auction is bid independent if bidder I's bid value should only determine whether the bidder wins the auction, but not the price. We select a sample B prime of B at random, independent from the bid values. We use the bids in B prime to compute the optimal bid threshold FB prime. FB prime is to maximize the revenue in B prime. Then, every bidder in B minus B prime whose bid value is over FB prime wins. Symmetrically, we use the bids in B minus B prime to compute the optimal bit threshold fb minus b pi that maximizes the revenue in b minus b pi. And every bidder in b prime whose bit value is higher than fb minus b pi wins. Random sampling auction, no matter the single price version or the multiple price version, are competitive. Indeed, there are 15 competitive in the worst case and 4 competitive for a large class of instances where there are at least 6 bits are as good as the optimal sell price. There are a series of improvements on random sampling auctions. Goldberg and Hartline extend the scope of single digital product with unlimited supply to multiple products with unlimited supply. Given a set of bits, they show that the bidder optimal product assignment given the bits and the optimal sell prices can be determined by solving the integer programming problem as shown in the slide. Then, we can solve the optimal pricing problem in the following random sampling auction. Let B be the set of bidders. First, we obtain a sample B prime of bidders. Second, we compute the optimal sell prices for B prime. Last, we run the fixed price auction on B minus B prime using the sales price computed in the previous integer programming problem. All bidders in B prime lose the auction. The random sampling auction is shown truthful and competitive. Most of the proposed auctions for digital goods with unlimited supply are randomized auctions. Goldberg et al. Show that no deterministic auction can be competitive. Agawa et al. Later find out that the result does not hold for asymmetric auctions. In a symmetric X-AND auction, buyer's preference parameters are drawn from a symmetric probability distribution, and thus there exists a symmetric equilibrium if an equilibrium exists at all. In an asymmetric auction, each buyer has the same information about the product but a different opportunity cost of obtaining the product. That is, bidders' valuations are drawn from different distributions. Agawa et al. Give an asymmetric deterministic auction that can approximate the revenue of any optimal single price sale in the worst case. Indeed, they develop a general randomization technique to transform any randomized auction into an asymmetric deterministic auction with approximately the same revenue. The general idea follows the deterministic maximization flow solution to the well-known hat problem. One drawback in random sampling auctions is that some bidders may lose even they make bids higher than some winning bidders do. Since the bidders in B prime and B minus B prime use different thresholds in one product version, and all bidders in B prime loses in the multi-product version. Goldberg and Hartline establish a fundamental result. An auction cannot be at the same time truthful, competitive, and envy-free. They also explore possible trade-offs between truthfulness and envy-freeness based on the consensus revenue estimate. Specifically, using a similar idea in combinatorial auctions with single parameter agents, we can relax the truthfulness requirement by requiring being truthful with probability 1 minus epsilon and always guarantee envy-free. The auction is highly truthful when epsilon approaches 0 and the number of winners in the auction approach infinity. The other type of auctions relaxes the envy-free requirement to being envy-free with probability 1 minus epsilon and guarantees that truthfulness. Both auctions are competitive and the probability is over random coin tosses made by the randomized auction mechanism and not the input. In addition to potentially unlimited supply, another important feature of digital goods is that a digital good such as a movie and a song may be sold repetitively. Therefore, auctions on digital goods may run continuously instead of only one round. Moreover, customers may want to have a prompt answer to their bids. Online auctions are designed to address the setting where different customers bid at different times. The auction mechanism has to make a decision about each bid as it arrives. An online auction is insensitive compatible if the bidders are rationally motivated to reveal their true valuation of the object. Levy and Neeson showed that an online auction is insensitive compatible if and only if it is based on supply curves under the assumption of limited supply. That is, before it receives the ith bid, BIQ, it fixes the supply curves, PIQ, based on the previous bids. And the quantity Qi sold to customer I is the quantity Q that maximizes the sum of Bij minus Pij. J equals 1 to Q. And the price paid by I is the sum of Pij when J iterates from 1 to Q. They also propose insensitive compatible auctions for limited supply. To tackle the challenge where there is unlimited supply, Joseph et al. Point out that supply curves are not available anymore in this situation. Instead, they proposed an extremely simple incentive compatible randomized online auction. For each bidder I, it picks a random number t between 0 to log h floor and set the price threshold to Si equal to 2 to the power of t, where h is the ratio of the highest valuation against the lowest valuation among all bidders. This auction is shown to be O log h competitive. The auction mechanism can be further improved to achieve even better incentive compatibility. Specifically, we can divide a sequence of bits B1, B2 into L buckets, where L equals log h floor plus 1, such that the bucket Bj contains the bits with indexes in the range of 2 to the power of j to the 2 to the power of j plus 1. The weight of bucket Bj is the sum of bits within Ij. That is, Wj equals the sum of I in this bucket Bj. A new bidder can choose one of the buckets at random with the probability proportional to the bucket weight and pays the price of the lowest bid of the bucket. The price Si that bidder I pace follows the probability distribution of PR Si equals J equals to Wj over the sum of Wr to the power of D. This auction is shown to be competitive. By setting D properly, the auction can be shown to log h square root exponential competitive. In summary, as revenue maximization plays a fundamental role in pricing digital products, we reviewed the three major streams of revenues for digital products, namely money, information and privacy, and time and attention. Then, we visit the bundling and subscription planning for digital products, which echoes the opportunities and challenges due to low replication costs of information goods. Auctions are widely used in pricing digital products. We review some basic types of auctions and their applications in digital products, including sponsored such auctions, auctions with unlimited supplies, envy-free auctions, and online auctions. Some ideas employed by pricing digital products are also used in pricing data products. This will be discussed in the next section. Thank you.